August 27, 1939. Marin Airfield, Germany. The shriek that split the morning air defied every assumption aviation experts held about powered flight. From the cockpit of the Hankl He-178, test pilot Eric Varsett felt vibrations unlike anything produced by propeller-driven aircraft. Behind him, instead of pistons hammering in cylinders, a continuous roar emerged from Hans von Ohein's He-S-3B turbojet engine. No propeller blades carved through air. No reciprocating motion converted fuel into thrust. Instead, compressed air mixed with fuel in a combustion chamber that burned continuously, expelling exhaust gases through a nozzle that pushed the aircraft forward through pure reaction. The mathematics of aviation were being rewritten in fire and compressed air. Within minutes of takeoff, Varsett realized he was piloting the future. The steady thrust, the absence of propeller torque, the smoothness of continuous combustion versus explosive piston cycles. Everything felt different. What neither Varsett nor the German engineers watching from the ground understood was that this maiden flight would trigger the most profound transformation in aviation history. A revolution that would render every piston-powered fighter obsolete within a decade and eventually carry millions of passengers across oceans at altitudes and speeds impossible for conventional aircraft. The journey to this moment had begun not with aviation pioneers, but with scientists pursuing abstract theories about thermodynamics and fluid flow. In 1930, Frank Whittle, a young Royal Air Force officer studying at Cambridge University, submitted a patent application for what he called a turbojet engine. His professors dismissed the concept as impractical. The Air Ministry rejected his proposal for funding. Traditional aircraft manufacturers showed no interest in an engine that seemed to violate common sense about propulsion. Whittle's revolutionary insight challenged fundamental assumptions about flight. Since the Wright brothers' first flight in 1903, aviation had relied on propellers driven by internal combustion engines. These systems worked by converting the reciprocating motion of pistons into rotational motion that spun propeller blades, which grabbed air and pulled aircraft forward. Whittle envisioned something radically different. Air would be drawn into a compressor, mixed with fuel in a combustion chamber, where it burned continuously, then expelled through a nozzle to create thrust directly. The theoretical advantages were compelling. Jet engines would operate more efficiently at high altitudes, where thin air caused propeller performance to degrade dramatically. They would produce steady thrust without the vibrations and mechanical complexity of piston engines. Most significantly, they would enable aircraft to fly faster than any propeller-driven machine could achieve. The practical challenges seemed insurmountable. Meanwhile, in Germany, Hans Pabst von Ohain was pursuing similar concepts independently. Working at the University of Göttingen under Professor Robert Pohl, von Ohain had developed his own theories about gas turbine propulsion for aircraft. Unlike Whittle, who struggled to find financial backing in Britain, von Ohain attracted the attention of Ernst Hankl, an aircraft manufacturer willing to invest in revolutionary technology. By 1936, von Ohain was developing prototype jet engines with substantial funding and engineering support. The contrast between British and German approaches would prove decisive. Whittle, despite his technical brilliance, worked with minimal resources. His company, Power Jets Limited, operated from a small facility with inadequate funding and limited manufacturing capability. The British government, focused on immediate military needs, showed little interest in experimental engines that might not be ready for years. German investment in jet technology was systematic and well-funded. Hankl committed substantial resources to von Ohain's research. The German Air Ministry, while initially skeptical, provided increasing support as prototypes demonstrated potential. By 1937, von Ohain's He-S-1 engine achieved successful ground testing. The He-S-3B that would power the He-178's first flight incorporated lessons learned from earlier failures. German metallurgy, among the world's most advanced, provided materials capable of withstanding the extreme temperatures and stresses inside jet engines. Specialized steel alloys and precision manufacturing techniques developed for other industries found application in turbine blade production. The technological challenges were formidable. Jet engines required components to operate at temperatures exceeding 1,500 degrees Fahrenheit, while rotating at speeds approaching 10,000 revolutions per minute. Turbine blades had to maintain structural integrity under centrifugal forces that would tear apart conventional materials. Combustion chambers needed to burn fuel efficiently across a wide range of operating conditions. Compressor sections had to pressurize incoming air to ratios that previous machinery had never achieved. Traditional aircraft engines operated on well-understood principles refined over decades. Jet engines demanded advances in multiple scientific disciplines simultaneously. Thermodynamics, fluid mechanics, materials science, and precision manufacturing all required breakthroughs before practical jet propulsion became possible. The interdisciplinary nature of the challenges explained why progress came slowly despite obvious theoretical advantages. As the WWII-178 completed its historic flight on that August morning, aviation experts worldwide remained unaware that everything had changed. The German military, despite witnessing successful demonstrations, initially showed limited enthusiasm for jet aircraft. Existing piston-powered fighters seemed adequate for current needs. The complexity and cost of jet engines appeared unjustified when proven technology was readily available. This conservative response reflected broader patterns in military procurement. Revolutionary technologies often face resistance from institutions invested in existing systems. The German Luftwaffe had achieved remarkable success with conventional aircraft. Messerschmitt Bf-109s and Focke-Wulf 190s dominated European skies. Why risk unproven jet technology when current aircraft were winning battles? Similar skepticism prevailed in Britain and America. When reports of German jet aircraft development reached Allied intelligence services, many experts dismissed them as propaganda or experimental curiosities with no practical military value. The assumption that jet engines were too complex, too unreliable, and too fuel-hungry for operational use persisted even as evidence mounted that Germany was making significant progress. The outbreak of World War II in September 1939 initially accelerated conventional aircraft development while delaying jet engine research. Military priorities focused on producing large numbers of proven fighters and bombers rather than developing experimental technologies. Resources flowed toward expanding production of existing designs rather than funding research programs with uncertain outcomes. Yet warfare would ultimately prove to be jet technology's greatest catalyst. As the conflict intensified, performance limitations of piston-powered aircraft became increasingly apparent. Fighter speeds approached the theoretical maximum achievable with propellers. High-altitude performance remained poor due to reduced air density. Engine complexity increased as manufacturers added turbochargers and other systems to maintain power at altitude. By 1941, German engineers were achieving remarkable progress with operational jet aircraft. The Messerschmitt Me-262, powered by Jumo 004 turbojet engines, demonstrated performance capabilities that exceeded anything Allied forces possessed. Maximum speeds approached 540 miles per hour, compared to 400 miles per hour for the fastest piston fighters. Service ceilings reached altitudes where Allied bombers operated with impunity. British jet development, despite Frank Whittle's early theoretical work, lagged behind German efforts due to inadequate funding and institutional resistance. The Gloster E-28/39, Britain's first jet aircraft, didn't achieve first flight until May 1941, nearly 2 years after the German He-178. Even then, the program received limited support from military authorities focused on immediate wartime needs. American jet development began even later. The United States Army Air Forces, confident in their existing aircraft designs, showed minimal interest in jet technology until reports of German jet fighters became impossible to ignore. Bell Aircraft received contracts for experimental jet aircraft in 1941, but development proceeded slowly due to lack of urgency and limited understanding of the technology involved. The performance advantages of jet propulsion became undeniable as test flights accumulated data. Jet engines delivered thrust that remained constant regardless of altitude, unlike piston engines that lost power as air density decreased. The absence of propellers eliminated the shockwave formation that limited high-speed flight. Mechanical simplicity, despite manufacturing complexity, promised improved reliability once production techniques matured. The transformation accelerated as war demands pushed engineering boundaries beyond peacetime constraints. German factories began producing WW004 engines in quantities that demonstrated jet technology's transition from laboratory curiosity to operational reality. Each engine required 375 hours of skilled labor and exotic materials that strained Germany's industrial capacity. Yet production reached nearly 6,000 units by war's end. The manufacturing challenge revealed both the promise and limitations of early jet technology. Meanwhile, Allied engineers who had initially dismissed jet propulsion found themselves racing to close a technological gap that threatened air superiority. Frank Whittle's power jets received emergency funding as British authorities realized German jets posed existential threats to bomber operations. American manufacturers began crash programs to develop indigenous jet engines, but the learning curve proved steeper than anticipated. The complexity of jet engine manufacturing exceeded anything the aviation industry had previously attempted. Turbine blades required precision machining to tolerances measured in thousandths of inches. Heat-resistant alloys demanded specialized foundries and metallurgical expertise that few companies possessed. Quality control standards far exceeded those for conventional engines, as single-component failures could destroy entire power plants within seconds. General Electric, leveraging its experience with steam turbines and electrical generators, emerged as America's leading jet engine manufacturer. The company's ability to work with high-temperature materials and precision rotating machinery translated effectively to aircraft propulsion. By 1944, GE was producing engines that powered experimental American jet fighters competitive with German designs. The operational debut of jet fighters transformed aerial combat in ways that conventional aircraft couldn't match. German Me-262s attacking Allied bomber formations demonstrated speed advantages that rendered traditional fighter escort tactics obsolete. American P-51 Mustangs and British Spitfires, despite exceptional performance for piston aircraft, couldn't intercept jets in level flight. The psychological impact on Allied aircrews was profound and immediate. Combat experience revealed jet engines' operational characteristics under wartime conditions. Fuel consumption exceeded piston engines by substantial margins, limiting mission duration and tactical flexibility. Engine life measured in hours rather than hundreds of hours demanded constant maintenance and frequent replacement. Acceleration from idle to full power required careful technique, as rapid throttle movements could cause compressor stalls or engine fires. Yet performance advantages outweighed operational challenges for pilots who mastered jet aircraft handling characteristics. The absence of propeller torque eliminated takeoff difficulties that plagued high-powered piston fighters. Smooth power delivery improved gunnery accuracy during air-to-air combat. High-altitude performance enabled operations in atmospheric regions where conventional aircraft struggled to maintain control. British jet development gained momentum as Rolls-Royce applied its aerospace expertise to turbine technology. The company's Welland and Derwent engines powered Gloucester Meteor fighters that entered combat in 1944. While less advanced than German engines in some respects, British designs emphasized reliability and manufacturability over maximum performance. This philosophy would prove prescient as jet technology matured. The end of World War II brought captured German jet engines and technical documentation to Allied nations hungry for advanced propulsion technology. Teams of engineers studied WW004 and BMW003 engines, reverse engineering design principles and manufacturing techniques. This technology transfer accelerated post-war jet development in Britain, America, and the Soviet Union by years. Soviet engineers with access to German facilities and personnel in occupied territory achieved rapid progress in jet technology. The Klimov VK-1 engine, based on British designs provided under wartime agreements, powered MiG-15 fighters that would challenge American jets in the Korean War. The global spread of jet technology ensured that future conflicts would be fought entirely with turbine-powered aircraft. Commercial aviation remained wedded to piston engines through the late 1940s, as airline executives questioned jet technology's economic viability. Fuel consumption, maintenance costs, and passenger capacity seemed inadequate for profitable operations. The de Havilland Comet's entry into service in 1952 as the world's first jet airliner demonstrated commercial jet travel's potential, while revealing design challenges that would require years to resolve. Engineering advances driven by military requirements gradually addressed jet technology's early limitations. Improved materials enabled longer engine life and reduced maintenance requirements. Better fuel control systems enhanced throttle response and operational reliability. Aerodynamic refinements increased efficiency and reduced noise levels that had made early jets unsuitable for civilian airports. The Korean War provided the first large-scale combat between jet aircraft as American F-86 Sabres battled Soviet-designed MiG-15 in aerial combat engagements that tested both aircraft and pilot capabilities. Performance similarities between opposing jets meant that pilot skill and tactical innovation determined outcomes more than technological superiority. The era of jet air combat had truly arrived. Manufacturing techniques evolved rapidly as production volumes increased and competition intensified. Investment casting processes enabled complex turbine blade geometries impossible with conventional machining. Specialized testing facilities verified engine performance under conditions simulating high-altitude flight. Quality control procedures eliminated defects that could cause catastrophic failures during operation. By 1955, jet engines had achieved reliability levels approaching those of mature piston power plants, while delivering performance impossible with conventional propulsion. Commercial airlines began ordering jet transports in quantities that promised profitable operations. Military services worldwide were transitioning entirely to jet aircraft for fighter and bomber roles. The transformation from experimental curiosity to dominant technology was complete. The airlines that had hesitated through the early 1950s found themselves racing to acquire jet transports as passenger demand for faster travel overwhelmed operational concerns. Pan American World Airways, under Juan Trippe's leadership, placed orders for Boeing 707s and Douglas DC-8s that would transform international travel from multi-day ordeals into single-day journeys. The psychological barrier of crossing oceans in hours rather than days shattered forever on October 26, 1958, when BOAC's Comet 4 completed the first scheduled transatlantic jet service between London and New York. What passengers experienced aboard these early jet airliners defied everything they understood about commercial flight. The absence of propeller noise and vibration created cabin environments approaching library quietness. Smooth acceleration replaced the lurching power delivery of piston engines climbing through turbulent air. Most remarkably, jets climbed rapidly above weather systems that had tormented travelers for decades, reaching altitudes where blue skies and sunshine prevailed regardless of ground conditions. The economic transformation proved equally revolutionary. Airlines discovered that jets could complete 3 round trips across the Atlantic in the time required for 2 piston aircraft journeys. Higher speeds translated directly into increased aircraft utilization and revenue generation. Passenger capacity improvements, while modest initially, combined with speed advantages to deliver productivity gains that justified higher acquisition costs. Boeing's 707 program represented American industry's most ambitious commercial aviation project since the dawn of flight. The company invested $16 million of its own funds developing the prototype, betting the corporation's future on jet transport demand that existed largely in marketing projections. When the prototype first flew in July 1954, Boeing had no firm orders and faced skepticism from airlines comfortable with proven piston transports. The engineering challenges of scaling jet technology to airline requirements exceeded those faced by military aircraft designers. Commercial jets needed to operate reliably for thousands of hours between major overhauls. They required fuel efficiency that made intercontinental flights economically viable. Most critically, they demanded safety levels that would convince passengers to trust their lives to unfamiliar technology. Pratt & Whitney's JT3C turbojet engines powering early 707s consumed fuel at rates that shocked airline accountants accustomed to piston engine economics. A transcontinental flight burned approximately 15,000 gallons of jet fuel, compared to 8,000 gallons for equivalent piston aircraft. Yet the speed advantage enabled airlines to complete more flights daily, spreading fixed costs across additional revenue opportunities. Douglas Aircraft's DC-8 development paralleled Boeing's efforts with subtle but significant differences in design philosophy. Where Boeing emphasized proven military jet experience, Douglas focused on optimizing commercial operations from the beginning. The DC-8's larger passenger capacity and longer range capabilities attracted airlines planning high-density routes and intercontinental services. European manufacturers struggled to compete with American jet transport dominance despite pioneering commercial jet technology with the Comet. Sud Aviation's Caravelle, featuring rear-mounted engines and triangular windows, offered innovative solutions to jet transport challenges but lacked the range and capacity for intercontinental operations. The concentration of global airline demand on long-haul routes favored American designs optimized for those missions. The Federal Aviation Administration faced unprecedented challenges certifying aircraft, whose performance capabilities exceeded existing regulatory frameworks. Jet transports operated at altitudes and speeds where conventional flight rules proved inadequate. Air traffic control systems designed for slower aircraft struggled to manage jets descending from 35,000 feet at speeds approaching 600 miles per hour. Pilot training programs required complete restructuring to address jet aircraft handling characteristics that differed fundamentally from piston transports. Throttle response delays meant power changes had to be anticipated rather than reactive. High-speed approaches demanded precise energy management as jets couldn't quickly shed excess speed. Engine failure procedures emphasized immediate recognition and response, as jet engines provided less warning before catastrophic failure than piston power plants. The noise impact of early jets created community opposition that threatened airport operations worldwide. Residents near major airports experienced sound levels that made conversation impossible during takeoffs and landings. Local governments imposed restrictions that forced airlines to modify flight paths and operating procedures. The industry recognized that noise reduction would determine jet aviation's long-term viability. Military jet development accelerated through the 1950s as Cold War tensions demanded aircraft capable of intercepting enemy bombers at any altitude or speed. The Century Series fighters, including the F-100 Super Sabre and F-104 Starfighter, pushed jet technology towards supersonic performance that required advances in aerodynamics, materials, and propulsion systems. Afterburning technology emerged as military engineers sought maximum performance from jet engines. By injecting fuel into exhaust streams and igniting it behind the turbine, afterburners could double engine thrust for short periods. This capability enabled supersonic flight and rapid acceleration, essential for air-to-air combat, though fuel consumption rates made afterburning impractical for civilian applications. The development of turbofan engines represented the next evolutionary leap in jet propulsion. Instead of expelling all airflow through the combustion chamber, turbofans used large front fans to move additional air around the engine core. This bypass air provided thrust more efficiently than pure jets while reducing noise levels that had plagued early turbojets. Rolls-Royce's Conway engine, powering later versions of the Boeing 707 and Douglas DC-8, demonstrated turbofan technology's commercial potential. Fuel consumption improvements of 15 to 20%, combined with significantly reduced noise, made turbofans attractive to airlines facing both economic pressures and community complaints about jet noise. From that first shriek over Marin Airfield to the turbofan engines powering today's airliners, jet propulsion transformed aviation through relentless engineering determination, rather than sudden breakthrough. Every flight you take carries the legacy of wartime innovation, manufacturing revolution, and technological persistence that turned theoretical impossibility into everyday reality. The next time you hear that familiar whine of jet engines spooling up for takeoff, remember the scientists, engineers, and test pilots who literally rewrote the physics of flight itself.